Hey, welcome to this lecture on system of linear equations consistency test. So the previous lectures we've done on linear equation systems, we've covered the broad systems uh, of, of solutioning. We saw the row method, then we saw the column method, and of course we also did see the matrix methods for solving a system of linear equations. Now, uh, what this lecture will do is this will give you the broad framework to understand uh, the concept of consistency, the possibilities that exist in a system of linear equations for consistency, and we'll see why all of what we talked in the past in terms of the solutions, that's really a special case of the larger options available. So what is consistency? If you take a system of linear equations, when you think about it, there are really two or three things that can happen. One is that your system will be consistent, which case you have a unique solution, or you can have infinite solutions. Both these cases you say that the system is consistent. Then the other possibility is that the system is inconsistent, where you have no solution. Now, what are you seeing on the right side here? This is really the geometric interpretation of of this. So, when you say you have a unique solution, you plot uh, the, the the systems of equations here, and then they converge at a point, and that is called your unique solution. Now, on a two-dimensional system, this is the way it happens. For a three-dimensional system, you will get planes, and the point where those planes converge, that would be your solution coordinates. Now, for the case of infinite solutions, what you get is you have you would express the equations for the variables x and y in terms of z. If it is a three-variable system, then you would express x and y in terms of z, and then your solution set would be x of z, y of z, and z, and then that's when you put it in this construct, you are essentially looking at the solution coordinates as a function of z. So that means that for each value of z, you get solution coordinate one, 2, and such. So that means that that is only limited by the number of values of z, which effectively means you have an infinite solution set. Now the third possibility that we saw that we see is that you have no solution, where the system looks something like this. You have a couple of parallel lines, and therefore there is no convergence, and thus the solution set is no solution. Now this is really the concept of consistency. Now, as I said at the beginning of this lecture, whatever we saw in the when you try to run a system of linear equations through solution without doing the consistency test, you are effectively you would be able to solve it using the standard approaches only where you have this case, that is consistent unique solution. Because when the system does not have a consistent and unique solution, and the case where you have infinite solutions and where you have no solution, then your system your system suffers from what's called a solution breakdown. So and then the way to go about solving uh, these two, that would first require you to reduce the system into a solvable state and then attempt a solution. Uh, let's run through the, the consistency tests in greater detail now. So the professional approach to solving for consistency, for testing for consistency, is based on what's called the Rouche's theorem. Now, the Rouche's theorem. So this is how the Rouche's theorem goes. So assume that your system of linear equations can be represented as follows algebraically: a11x, a12x, a13. So let's say this is x1, x2, or you can put it as y. It doesn't matter. X3, a1 and xn equal to k1. So similarly, a21 till a2 and xn equals k2, and then am1, amn, xn equal to k. So here you have a system of m equations in n unknowns. So this is an m by n system, and this is your this is what you call your constant vector. Constant vector. Now a here, a that you see here, this is your coefficient matrix, and k is called augmented matrix. So k is essentially the coefficient matrix augmented with the constant vector. Now Rouche's theorem makes use of the concept of ranks. Now what is the rank? Now we say that the rank of A is R if the determinant of the vector A that is not equal to 0. So what you'll do is you'll calculate the determinant for this matrix, and if that is not equal to 0, then you can say that the rank of A will be equal to R. So in this case, R would be so when you take this matrix and you take its determinant that is not equal to 0, then the largest square matrix that can be drawn out of this, that would be your that would be R. So if we assume that the number of variables and the number of equations is the same, then R will be equal to n if this matrix is not equal to 0. So the way to go about thinking about rank is, it's the simplest way is like this. Suppose that you use elementary row transformations and column transformations to reduce this this matrix to the largest non-zero square matrix that you can draw out of it, which means that you get something like this. I of R 0. So these are zeros. These are all rows where columns where you have 0, 0. You have zeros here. Similarly, you have zeros here. Now the largest identity matrix IR, I hope this is clear, that you can draw out of A, this is called the rank of A. Similarly for K also, you derive the rank using the same approach. Now what Rouche's theorem says is that if R is not equal to R dash, then the system is immediately inconsistent. Bang. That is, if the rank of your coefficient matrix varies from the rank of the augmented matrix, then you can be sure that the system is inconsistent. Now here we note that we are talking about first a known homogeneous system, which means that these are not equal to 0. That is the case we are first dealing with, and this here we would deal with the case where each of the element k is equal to 0. So let's first look at k not equal to 0. That is a non-homogeneous system. So then in the non-homogeneous system where R is not equal to R dash, that is a case where where that will happen, then the system is inconsistent. Now if R equal to R dash, then the system is consistent, and if that value is equal to n, which is the number of variables, then you will have a unique solution. And if R is less than n, then you have infinite solutions expressible as R unknowns in terms of n minus R that is a remaining number of the variable parameters. Now, for a homogeneous system, always R will be equal to R dash. That is this possibility, that is where system is inconsistent. This for a non-homogeneous system, this does not exist. So the system will always be consistent. Therefore, R equal to R dash, when that is equal to n, you will have only a single solution, a unique solution, which will be trivial. That is, each variable from x1 till xn will be equal to 0. Now, in the case where R equal to R dash is less than n, you have infinite solutions, which can again be expressible as n minus R parameters. The R unknowns can be expressed in terms of n minus R parameters. So this is now Rouche's theorem is a professional consistency test, because the concept of ranks and calculating it this way, it's very elegant and it's easy to think in these terms when you are doing math at a professional level. We'll see an example of how the Rouche's theorem is implemented using a modern computing package R. I'll show you an example of that once this theoretical the concept is demonstrated. Now, the second approach, or rather alternative approaches you have, is one is a matrix method, another is a Cramer's rule. Now, these are more of academic interest, because Cramer's rule, for example, becomes very weirdy, unwieldy to use once you cross the order of 3. But nevertheless, it might help to understand from an academic perspective. So essentially, what the Cramer's rules, the approach says is that if your determinant of the coefficient matrix is not equal to 0, then the system will be consistent. But if that is equal to 0 and each of the the a1 to an determinants is 0, then the system may or may not be consistent. And whether it's consistent or not, what you would typically do is you take so if it's a three equation system, you'll take 2 equations and then you will calculate. So you have 3 equations here, you'll take 2 of that, and what you will do is you will express x and y there in terms of z, and then once you get x and y in terms of z, that you would do the solution will come through, of course, through the Cramer's rule method, and then you will substitute that into your third equation, x, y, z, and if it satisfies that, then you know that the system has a unique solution. But otherwise, if it doesn't satisfy, then the system will be inconsistent. Now, the third case is your determinant is 0, and at least one of AJs. AJ, of course, refers to the determinant matrix with the jth column replaced by the constant vector. And if that is one of that, at least one of that is not 0, then the system will be inconsistent, because you are effectively getting a 1 by 0 form. So now the matrix method is it's very similar in terms of the approach, but you might be interested to know that the Rouche's theorem that is based on the matrix method internally. But Rouche's theorem is, of course, it's clearer, and it's a more elegant way, a straightforward way to think about consistency. But for matrix method, this is the way it goes. The determinant is not equal to 0, again system is consistent with a unique solution, and if it's equal to 0 and the adjoint of A into B equals 0, then you have the 0 by 0 form, and that can then be reduced down to come up with a case for infinite solutions. And again, where you have the determinant equal to 0, the coefficient determinant equal to 0, and this adjoint of A into B, the term is not equal to 0, you have the 1 by 0 format, and therefore the system is inconsistent. Now, for a homogeneous system, you have a non-trivial solution if and only if the determinant is equal to 0, and when that is not the case, you have only the trivial solution. So let's see an example of how you implement the consistency test using the Gauss elimination method and with the Rouche theorem based consistency. So this is, I have done this in the solution using R. Uh, so this is your system of equations here: x plus 2y plus z equals 7, x plus 3z equals 11, 2x minus 3y equals 1. And what you would do is you would first calculate the coefficient matrix. Now, before we go into that, we talk a bit about R. So R is it's a beautiful math package for those of you who are not aware of it. And what it does is it gives you various packages that are customized for math functions. So if you want to do matrix functions, higher order matrix functions, you can use a Pragma library. So that has to be installed. So the installation will be done using the install dot packages, and then you will put Pragma. So when you do Pragma, this would install the Pragma library, and then you invoke that library here. And once you have invoked it, the way you would implement this would be, first you have to input the coefficient matrix, which is what you're doing here. Matrix 1, 2, 1. You see that corresponds to the coefficients here. Then 1, 0, 3, 2, minus 3, 0, and 5 row. If you put this as true, this would get populated this matrix. That's what you're seeing here. And this is nothing but this is your coefficient matrix. The one that we talked about. So I hope this really brings to life this theory here. So this is your coefficient matrix, and this is your augmented matrix. This is really what you're seeing here. So to get the augmented matrix here, what you'll do is you'll first input the constant vector 7, 11, 1. This is your constant vector, and then you will bind this matrix to this matrix at the column level by using the cbind function, and then you look at this. This would be your augmented matrix. Now, the next thing we do is, now the Rouche theorem says that you have to test for the ranks. You have to see whether the ranks are the same and equal to the number of variables. Now in this case, the number of variables n is equal to 3. You have x, y, z, and you find out the rank of this matrix using QR function. QR, okay, these are all there in the Pragma library once you have invoked it. So the rank of A is 3 as per R, and the rank of K is 3, and that is of course equal to the number of equations, the number of variables. And therefore, as per the Rouche theorem, this system R equal to R dash, that's equal to n, you have a unique solution. So we know that this is a unique solution, and now we proceed to solve this. Now the case where you do not have a unique solution, where the system where R equal to R dash is less than n, there are additional operations you need to do in terms of reducing the the equation to a solvable state, and that is something which that I will cover that in the tutorial that I have planned, which is much more detailed in Udemy and Skillshare, etc. I've gone through detailed examples of this, of this concept. Now, okay, let's come back to this. Now, the case where you have a unique solution. Now, then the next step would be, what you do is you have to solve this. And the way to solve, if you remember from the Gauss elimination method, is that you will apply systematically row and column transformations. You would apply row transformations to the augmented matrix to arrive systematically at the triangular form where you have pivots corresponding to your to the equations, and then uh, the standard Gauss elimination method uses what is called the lower triangular matrix form, where these are zeros and these would have non-zero values. But the approach that R uses is a more customized version of this. What it does is, using further transformations, it reduces this also to the trivial state. So essentially, you get something like this. Just the diagonals would be 1, 1, 1, and then you would have whatever comes here. That would effectively be your solution. So that is the approach that R uses through the RF function, which is what you're seeing here. You have an RF on the augmented matrix, and this is what you get here. You get this. So this is a way to interpret this. And when you do so, this helps you to save the labor of back substitution, because you're straight away getting x, y, and z here. So when you substitute those back, whatever you're getting on the right side, that would be your solution. I'll just add that one way to use R is on a black box model, where you can just go ahead and use these functions, the functions that are made available through the package, and then you can just get the solutions. But keep in mind that this is purely a black box model, and unless you know the theory, and getting to understand the theoretical framework and knowing why why the answer that you're getting is really the solution. In this case, 2, 1, 3, why that's a solution, and understanding it in depth, that has its benefits. Because for example, the case where you do not have a unique solution and you want to do further manipulations with the with the solution system, and then to really to get to understand why you are getting a solution like this, the underpinnings of of what goes on below the surface of what you see on a system such as R. You really need to study the theory, and that has its benefits. But for this purpose, I'd say this should give you a good demonstration of Rouche's theorem and the consistency test as implemented in a modern package such as R. And of course, this would be I hope it provides you a concise summary of of the consistency test as such. Thank you.